Alright guys, welcome to another lecture of digital control system, and today we are going to solve the example that is related to the previous lecture. And in the previous lecture we actually covered the design based root locus, in which we covered the following points: the calculation of angle and magnitude criterion, basic rules for constructing the root locus, the pole zero cancellation impact, and the impact of sampling frequency variation over the digital system, as well as the impact of the sampling frequency over the transient response. And today we are going to solve the example in which we will be trying to control our system with the help of digital controller, and that controller will be constructed based upon the design based on the root locus. So let's move on. Alright guys, design a digital controller with the dominant poles that have the damping ratio of zeta that's equal to 0.5. the sampling time is 0.2 second, and the settling time is also 2 seconds. Also obtain the response of design digital control system for the unit step input, and also obtain the static velocity error for this whole given system. Alright, in this today's example we will try to illustrate the impact of this system that is being digitalized and is implemented without the digital controller, and after that we will implement this digital controller that the parameters are set according to the given conditions, and then we will simulate our system once again in order to realize that what's the impact of implementing the digital controller and without the digital controller. And you will be able to realize the difference between the system overshoot, the system settling time, the system response, and so on. And in the end we will be evaluating the static velocity error as well through this numerical analysis as well as the MATLAB simulation. So how we are going to do our work is, first of all I will be discretizing the system by considering the impact of my plant that is in S domain, and multiplied with zero order hold, and finally we will find out the digital controller. Since the system is cascaded with that of the zero order hold, so I just multiply the system, the plant, 1 over s into s plus 2 with that of the zero order hold, that is defined by this 1 minus e raised to power minus 0.2 of s divided by s, and after that we will take the z transform, and by taking the z transform as discussed by the previous methods in my previous lecture, we actually obtain the g of z for this whole plant. And it says that the system has 1 0 at z is equal to minus 0.8760, and the system is having the two poles at z is equal to 1 and z is equal to 0.6703. So okay, we can now place the poles and zeros defined by our open loop system g of z in the PZ map, and it says that there is one pole at this 1 z is equal to 1, and one pole at z is equal to 0.67, and there is one 0 at 0.8 something. The exact values are being defined above in the g of z. So now according to the given conditions, we have been defined that the point has been located with the values of the given in the term of zeta and all those conditions. Now we can easily find our exact point P is lying somewhere defined by these conditions if we are able to evaluate the magnitude from the origin and as well as the angle that is being mentioned. So we can easily track our point P using the polar coordinate system in this z plane, by marking the magnitude as well as the phase. So let's define the magnitude and the phase by the following equation. So from the magnitude criterion and the angle criterion defined in our previous lecture, we evaluated the formulas for the magnitude criterion to be as e raised to power minus t zeta omega n, that is natural frequency. We can also write it in the form of exponential if minus 2 pi zeta divided by 1 minus zeta square with that of the omega d over omega s, where omega d is the damping ratio and the omega s is the sampling frequency, and the angle criterion is defined by the settling time multiplied by omega of t. That's actually can be transformed as 2 pi omega d over omega s criterion, where actually we have mentioned the t in term of sampling frequency. That's why the omega s is being mentioned over here. Now let's try to find out the value of the natural frequency omega of n, so that we can easily evaluate the magnitude criterion. Since the defined settling time is 2 seconds and we know that t of s is actually equal to 4 over zeta omega, and zeta is being already defined in the question, that's 0.5. So by substituting all the values, we actually obtain the natural frequency to be 4 radian per second. Now we can also relate the natural frequency with that of the damping frequency omega of d, that's actually equal to omega n into 1 minus zeta square, and by placing the value of zeta we actually obtained that omega d is actually equal to 3.464. Similarly, we can also evaluate the sampling frequency defined by the sampling omega s, that's equal to 2 pi over t, and t is the sampling time that is already been defined in the question, that's 0.2 second, and it's actually 31.42. Alright, now in my previous lecture I actually told you that the number of samples should be in a range of 9 to 13 times of the sampling frequency. So you can easily calculate this fact from over here, that's the n, the number of sample is equal to the omega s over omega d, by substituting these values 31.42 divided by 3.464 and divide it, and we obtain n is equal to 32.4 divided by 3.46, that's equal to 9. So I think that is much satisfying answer, that our number of samples are in the suitable range. So from the magnitude and angle criterion, we can now substitute the values to find out the magnitude of the point that is to be placed in the unit circle, and as well as the phase. So let's find out. Alright, now after substituting and making the simplification, we actually obtain the magnitude to be 0.6703. That means the point is lying within the unit circle, and the angle is 39.69 degrees. So the point P has been located in the polar coordinate to be 0.6703 as the angle of 39.69 degrees, and we can also convert it into the rectangular coordinate, and it will become equal to 0.5158 plus the y-axis at 0.4281, that's the imaginary axis. You can also do this by using the scientific calculator and converting the polar coordinate into the rectangular coordinate directly in order to save your time. So from all the above calculations, we have finally located this point P, that is at 0.515 from the real axis, and is above the 0.428 in the lying the parallel to the imaginary axis. Now the next step is to calculate the angles between the zeros and the poles, and let's find out the contribution, and in reality it should be plus minus below the 180 degree. Now let's find out how much angle is being compensated with our system. Alright, we have to measure the angle of the 0, which is theta 1. We have to measure the angle of poles that is lying anti-clockwise in the location, that is theta 2 prime, and similarly the anti-clock angle of the other pole, theta 3 prime. And by subtracting the angles of all the zeros minus the angles of all the poles, we will be able to realize the contribution of our angle difference. So let's find out the theta 1. Alright, in order to find the theta 1, it's actually equal to the tan inverse over perpendicular divided by the base. So we have the perpendicular, that's actually equal to the 0.428, and divided by the base, which is the horizontal distance from this point to the point of the 0 location. Okay, now the critical point to be remembered is that some portion is being mentioned in the negative direction, and while the rest of it is mentioned in the positive direction. So you have to find out the overall location from overall distance, which actually means that from this point to let me mark over from this point to over here, it's actually being mentioned by B, and from the origin to the negative side of toward the 0 is represented by the negative directions, and it is minus of A. So that means the total distance is the subtraction of these 2 points. So that means the B minus into minus of A, that will become positive. So if you place the values, you will actually get 17 point something, just like 17.01 degree. So this is the angle contribution by the 0 at theta 1. Okay, now let's move toward the angle for the pole. Okay, our pole is at this distance 0.515 and 0.67, so it can be easily subtracted by B minus A formula, and whatever the incremental distance it becomes, just mention it in this equation. Okay, and the vertical distance at this point is once again 0.428. Now similarly, you can also evaluate the angle for the external side. That means you need to find out the this theta 2 prime. So it means that if you subtract the overall angle from this point to the second coordinate, that is 180 degree, if you minus your 180 degree minus the theta 2, you will be able to evaluate the theta 2 prime, which is the external side and the angle taken from the anti-clockwise direction. Now similarly, you can apply the same steps for the evaluation of theta 3 prime as well, and you will be able to evaluate all the angles from the poles contributions and as well as from the contribution for the zeros. Now when you do that math, you will be able to find out the angle of all the zeros minus the angle of the poles, and we have been observing that it's 231.26. However, the angle contribution should be 180 degree. So let's find out the difference of the contribution by subtracting our angle being produced by our system, and with that composition is actually obtained as minus 51.26. Now this means that if we are trying to implement the digital controller, that controller should compensate the 51.26 degrees in order to make the difference 0. So let's now design our digital controller with the given constraints. Now in root locus, generally we define our digital controller in the form of g of d of z, that's equal to k, which is the proportional gain, multiplied by z plus alpha and divided by z plus beta. That means that the controller has the 0 at z is equal to minus alpha and 1 pole at z is equal to minus beta. And in our previous topic, while designing the root locus, we clearly defined that in order to conclude your simplicity, we actually chose 1 0 of the controller that is equivalent to that of the pole of our given open loop system. That means that we have made one pole 0 cancellation so that we can reduce our maths, or we can reduce our steps for calculating the values of the digital controller that can actually compensate the 51.26 degrees. Alright, now by definition we need to calculate the value of the pole that can be located, so you can easily realize in the denominator of the controller that C is equal to minus of beta. So that means that it is negative and will be lying somewhere around in this location, but we don't know. So let's calculate it with reference to our this point, and we assume that 0.515 is the by given point, and we don't know what is the exact location of this point that is to be determined. Let's say this point is that negative b in this region. We don't know what is the exact value, but we do know that we need to produce the compensation that's actually equal to 51.26 degrees, that is being actually mentioned in our that is our desired compensation. And so this is our compensation with 51.26. we need to compensate this value, and we need to find out this point B. By solving this whole formulation, we are easily able to find out the value of B, that is given as B is equal to 0.236. so this means that this point will be over at somewhere. 0.236 is over here, and exactly this is the pole of the controller, and this is how we actually obtained. However, the 0 of the controller is being as well assumed as 0.67, so this is marked as over here in the black circle. So these are the values and parameters for our digital controller that will help us to compensate the 51.26 degree that is being produced by our system without implementing the controller. Now we have found finally the parameters of the alpha and beta, that are the zeros and poles of our controller. We need now to evaluate the value of gain that will help us to carry out our system, and by definition we know that the open loop impulse transfer function is defined by GD G of Z, and we can easily find out the value of gain K, and by just taking the magnitude theorem and apply it at the desired given point P, and it is always equal to 1. That is being told and discussed in the root locus rules for the construction. Now if you do that, if you place the point P in this open loop transfer function and set it equal to 1, you will easily find out the value of gain, that's equal to K is equal to 12.6. so this is the complete closed loop impulse transfer function for our given system that is having the required set of controller with all the characteristics that are being defined in the given question. And now let us simulate, and let us first of all find the step input response for the given system. The R of Z is set to the step input, and we know that the step input, the Z transform of the step input is by 1 divided by 1 minus Z inverse. So this is the final structure for our required system that is been excited by the step input. From here you can easily find out the output response C of k of t by just setting it equal to the partial fraction and take the Z inverse transform in the end, so you will easily find out the Ck of t. In the second part, it says that you need to find out the velocity gain k of v for the open loop system transfer function that is being defined by g of d c into g of z. Now if I substitute the values and set the limit approaches to 1, the k of v is being defined by 2.801. The steady state error is actually equal to the 1 over k of v, and the steady state error being present in our system is 0.35. so this is the whole system being controlled by the digital controller, and now we will simulate the system with and without the implementation of our digital controller. So let's move on.